Porto, Portugal.
Hello everyone. Thank you, Pascual, for this introduction, and thank you so much for inviting Atlantis to be here and to share our experience with the remaining participants. Okay, so I will start sharing my screen.
Sorry for reminding you that you have approximately 10 minutes. Okay, thank you.
Thank you. Sorry. Okay, I think that probably you already seeing the presentation. So, hello, my name is Andry Maykol Pinto. I'm an assistant professor at the Faculty of Engineering of the University of Porto, and also a researcher from INESC. I'm here today to talk a little about Atlantis. In Atlantis, we are addressing the relevancy of inspection, maintenance, and repair activities for offshore wind energy sector, since the offshore wind farms required higher efforts related to turbine maintenance and logistics. And this is a rising problem since the offshore wind farms that are operating, particularly in Europe, are relatively young. Nearly 80% of the installed capacity will remain in the first half of their design lives by 2028. So the project includes relevant stakeholders from the robotics sector, from the offshore wind energy market, as well as from the maritime industry. We have 10 partners, and Atlantis mainly address the scientific and technical challenges in this field, in particular a test facility and services for contributing to a seamless progression of robotic prototypes along the different TR level ranges, the development of new robotic platforms and autonomous driving features to improve the preservation of human life and safety, the enhancements related to operations perception capabilities of maritime robots to make them more suitable to operate in critical conditions at offshore wind farms, which are needed to reduce the costs of maintenance and to avoid catastrophic failures, of course. And finally, the acceleration of research and development of maritime robotics and the adoption of technology by, of course, end users. This project will establish a pioneer pilot infrastructure, which is particularly interesting for robotic developers, whose goal is to demonstrate the added value of technology in offshore wind farms. Stakeholders from the offshore wind energy sector will directly benefit from these demonstrations, from these validations, and in particular because of the technology uptake. Okay, here in Atlantis we are developing a pilot infrastructure that is formed by two locations. One is the coastal test bed and the other is the offshore test bed. I will not show the video because of the time constraints. Nevertheless, the coastal test bed will be located in the Lima River here in Portugal. It will be linked to local stakeholders from the offshore sector, and the offshore test bed will be located in the Windfloat Atlantic Park, which is an offshore wind farm formed by 3 floating turbines in the Atlantic Ocean. Okay. This windmill is owned by the WindPlus, and it will be used to validate, demonstrate technology in high TR levels. The Atlantis Test Center will constitute the first European test center capable of demonstrating robotic technology under extreme weather and sea state conditions, in particular because of the Atlantic Ocean. It is characterized by showcases and scenarios for inspection, maintenance, and repair activities that are being led by the industry. For instance, for inspection of blades and towers, inspection of transition pieces, repair of underwater floating protection systems, underwater monitoring over extended periods of time, underwater close range inspections, underwater monitoring of scour, operations supported by crewless vessels, and finally the optimization of robotic-based operations. Each scenario is addressing, of course, specific technical aspects of the inspection maintenance, and it enables distant robotic solutions to and services to reach technological maturity. These robotic solutions can be of different nature. For instance, the Atlantis Test Center will have scenarios for the operation of AUVs, UAVs, ROVs, ASVs, and different inspection, maintenance, and repair technology. I will not enter in many details for each scenario because we are publishing videos describing the specificities of each scenario, okay? If you want to know more, you just need to follow us on LinkedIn. The videos are being published in a periodic basis. At this point, videos of scenario 1 was also released. More than providing a test facility, we also provide services to both academia and industry, and these services will, of course, support the activities at the Atlantis Test Center. This is particularly interesting for everyone that wants to perform open sea experiments in a safe and cost-efficient manner. But of course, Atlantis project has amazing robots that will be demonstrated in different scenarios. We are increasing the TR level of robotic platforms to respond to industry-led challenges and problems. We are developing a new era for robotics-based O&M operations. I will just present a few examples of technology that being enhanced in Atlantis. The first is the ASV technology for multi-domain mapping. A perception and navigation solution can be installed in different small to medium platforms, and it will be able to recognize elements in the environment, for instance, for monitoring the scour, okay? We have a wide range of underwater vehicles. These vehicles can operate in different hazard scenarios for inspection, maintenance, and activities, from confined flooded mines, galleries, to flooded open pits, or even at dams. The performance of this technology will also be investigated in the Atlantis Test Center. We are using intervention AOVs for cathodic protection measurement for underwater structures, autonomous measurement of cathodic protection potential over surfaces, beams, and other structural elements of the floating structure, including the necessary surface preparation, cleaning with the rotating brush are being developed, okay? The estimation of the degradation level of the protection anodes, automatic 3D laser scanning of protection anodes, and reconstruction of the anode volume for the estimation of the volume loss over time is also being developed. We are also developing technology to enable long-term deployments of AUVs, for instance, a docking station with wireless charging and wireless communication. And regarding the AUVs, a set of advanced features foster the autonomy of these agencies, okay? Our goal, of course, is to reduce the need of human-based operations here. We are also developing technology to support offshore operations, making the robots more capable of perceiving and interacting with the scenario. For instance, an underwater imaging system for close-range inspections is being developed under Atlantis. This system is able to provide 2D and point cloud information that is very accurate. The information is perceived in real time, and it is robust to photometric issues. We already discussed this in the previous presentation, related to subsea conditions. And this is crucial for tasks that involve intervention, okay? We just saw that. Of course, we are developing other tools, for instance, for autonomous visual inspection of the floating structure. In particular, software for enabling close-range navigation, okay? This navigation techniques intends to, of course, facilitate the visual inspection, mainly through autonomous underwater vehicles, which are simply not used in this industry, okay, or by this industry. Also, a tool for mission definition, supervision is under development. It will provide live and historical information. It will facilitate operations for planning and control, and of course, operation analysis. Okay, this is quite relevant. It will also include an interoperability function for managing different by an unified command and data sharing, and of course it will be already ready for ROS 2. Okay. New algorithms for safe and precise underwater manipulation are being investigated. Okay, advances in this field will support the rise of new autonomous intervention techniques. So we have much more technologies. To get in touch, you simply need to follow us on LinkedIn. Atlantis is an initiative to provide an open, and this is relevant, an open offshore purpose experimental infrastructure aimed at promoting innovation among stakeholders, ICT researchers in Europe, okay? Both from the academia and the industry. We have, well, our idea is to cover different levels of TR levels, okay, from the most prototypes, let's say this, to the most commercial ones. So we have here the coastal testbed to support the development of recent technology, immature technology, and then we will have the offshore testbed that aims to demonstrate, provide confidence to the industrial sector, okay, about the ability of the particular technology to perform and perform well. So we offer real world demonstrations open to all communities. Small, medium enterprises, startup companies can easily access to the Atlantis Test Center services, okay. New players can gain credibility more easy since technology can be de-risked in safer conditions, okay? So if you have more questions, comments, please contact me by email. You can also follow us on LinkedIn, okay? So once again, thank you so much for this invitation, okay?
Thank you very much, Andry. So we'll leave all the questions and answers to the end of the session. So let's move on to the next presentation by Thomas Vogele, DFKI Germany, entitled DeeperSense, Deep Learning for Multimodal Sensor Fusion. Please, Thomas.
Okay, thank you very much. Can you hear me?
Yes.
Okay, so I will share my screen. Oh. So I don't see, can you see the slide, the first slide?
Yes, it's perfect. It's perfect.
Okay, great. So thanks, Antonio, for the introduction.
Yeah.
My name is Thomas Vogele. I'm a senior researcher at the DFKI Robotics Innovation Center in Bremen. And today I want to give you a short overview of the DeeperSense project. The long title for this project is Deep Learning for Multimodal Sensor Fusion. And it is a new project. So we started only at the beginning of this year. Can you see now slide 2? Yeah, okay. So I cannot present you results here. It's more, I can present you the idea of this project and what we hope to achieve in the next 3 years. It is a research and innovation action funded under Horizon 2020 with a budget of about 3 million euros. So it's not a very large project. And we also have not too large, but efficient, I guess, consortium. We have 7 partners, 3 research institutes, DFKI, University of Girona, University of Haifa in Israel, a small company, Kraken Robotics, specialized in sensors. And then we have end users like the German Interior Ministry, the THW, Technische Hilfswerk, and the Israel Nature and National Parks Protection Authority, and Tecnoambiente in Spain. So it's a well-balanced consortium. And what we want to achieve in this consortium and with this in this project is that we really want to significantly improve the sensing capabilities of underwater, and not only underwater robotics. And we want to do this in three use cases. The first use case is related to diver monitoring. So we want to enable systems that can look at divers and watch them doing their job and alerting the oversight crew if there are any problems. The second one is on AUV navigation in the coral reefs. So this means coral reef stands here for a complex and very delicate environment. So we want to enable AUVs to navigate much better in these coral reefs. And the third use case is on seabed mapping and seabed sediment and classification. The idea behind this whole thing, what we call intersensorical learning, was inspired by a paper from Christensen and Al, relatively recent paper on bat vision. They showed that a combination of artificial ears, acoustic sensors, optical sensors, and neural networks can enable these acoustic sensors to create images that are, like visual images, visual depth images. And we just took this idea and translated it, or it was inspired us to come up with our concept for this DeeperSense project. And to explain this in the training phase, what we want to do is we want to take a sensor, like for example, this sensor B, which is, for example, a sonar system, which has a sonar sensor which creates some kind of fuzzy data, and want to combine this with, for example, a high definition camera through a neural network, and then train the acoustic sensor, train the sonar to create pictures that are almost the quality of the high definition camera. So once the neural network is trained, then we can use the sonar to create much better images in an area, in a situation where, for example, a camera could not be used, like when it's dark or when it's very turbid or so. And this is the basic idea, to take two sensor modalities and use one as input and one as output, and create through a neural network, create the relations between these two. And we want to do this in three different application, or three different sensors, three different applications, really. Sound to vision, which is related to this diver monitoring, where we want to use sonar and high definition camera to see in turbid waters. Then the eagle eye, which we dubbed eagle eye, which is related to the moving in the coral reefs, where we want to use a forward-looking camera and a forward-looking sonar as a combination. And the third one is what we call smart bottom scan, where we want to use a side scan sonar and camera images from the sea bottom to enable better sea bottom classification. As I said, this is the idea, what we want to do. We are at the moment at the stage of conceptualizing this and setting up the training data. Of course, training data for all the deep learning algorithms, training data is the most important issue. And so we were trying to get training data in three different locations in our facilities in Germany, Israel, and Spain, but also in areas, in natural environments close to these facilities. And of course, we try to also create synthetic data, but we already found out it's not so easy to find simulations for these environments. So this is definitely a challenge to create the data. That's why when we have the data created, we want to share at least part of these data to the community through data repository. We are currently looking at options how to implement this, but some of these data at least will be shared with the community, and they will be used in our project for algorithm training in a three-step approach, three optimization and training cycles. And then more importantly, once the data sets are trained, once the artificial neural networks are trained, we want to validate them in field trials in 3 different natural environments. In Germany, we want to use the North Sea and also lakes around here in Bremen to validate them. In Israel, we're looking at the Mediterranean and at the Red Sea, where we have a lot of coral reefs available. And in Spain, we're looking at the Mediterranean to validate this data. And the final demonstration will be in Germany, in Starnberger See, so in 2.5 years' time, if everything goes well. The expected impact of this project, of course, is in the first side, it's to get these algorithms tested and field validated. So algorithms specialized for underwater robotics, but so they will enable underwater robots to perform better and in more complex environments. But of course, what we also want to do is to test this idea of intersensorical learning and to improve robotic perception in general. So not only underwater environments, but also in terrestrial air and space environments. And down the road, as I said already, we will publish at least parts of the training data sets and make them available to the community. So we hope to create some impact here also in the community and to push other initiatives in that way. And for this, we also want to have a close interaction with EU robotics, with the DIH networks, and with the community in general. Yeah, and I guess with this, I'm already at the end of the project. As I said, we are currently in the conceptualization phase. You will see results maybe in half a year or so. And we have a website. I forgot to put it on here, but you will find it through Google. And if you have any questions, please contact me. Thanks very much.
Thank you very much, Thomas. Very good presentation. Thank you. So let's move on to the next speaker, Gabriele Ferri from NATO STO-CMRE in Italy. And the title is INFORE, Interactive Extreme Scale Analytics and Forecasting.
Do you see the presentation? Hi, do you hear me?
Yes, I do.
And the presentation?
Yes.
Okay, so first of all, thanks Professor Pascal for the introduction, and
Welcome.
Thanks for the organizer for having given me the possibility to present 2 European projects we are working on, the INFORE and the Matrix project. I will start from INFORE. INFORE stands for Interactive Extreme Scale Analytics and Forecasting, and the idea is to handle the challenges posed by the huge data sets that now you are dealing with when you are dealing with application where you have real-time application, interactive extreme scale analytics and forecasting. So the final objective of INFORE is to develop a system that is flexible, pluggable, distributed, and above all, that can be configured using by a graphical tool with the idea of allowing also a not expert programmer to use this kind of object. And the system will be tested by the consortium in 3 different use cases. One use case from life sciences, one from financial world, and one for the maritime domain. we are working on the maritime domain use case that I will start talking right now. In the maritime domain, we want to bring the INFORE system in a maritime situation awareness application, essentially a coastal surveillance application. And the idea is to fuse, to use multimodal sensing and to fuse global view and local view based on a hybrid robotics network to integrate different sources of data to improve the MSA. So the global sensor that we use and in which marine traffic from Greece is leading together with the Democritos Institute will be a multispectral instrument from Sentinel satellite and SAR sensor from the Sentinel satellite. While the local view, as I said, is composed by a hybrid and cooperative robotic networks in which we have different two wave gliders equipped with passive sonar sensor, a fixed thermal and RGB camera, and finally a fast vehicle for final target identification. So all these data are sent to the INFORE system in which a fusion system based on machine learning and historical data, for instance, on the track of vessels on historical AES data, will be used for event detection that will trigger the actions of the network. So our task inside the project is the development of this network of silence, long endurance, cooperative passive sensing robots based on wave gliders surface vehicle. Why? Because they are early. They can provide a early stealthy vessel detection. They can offer persistent coverage of an area. They are silent, so we can use passive sonar processing. And they can share their data and cooperate with the onshore thermal camera. But these kind of robots have limited speed and can provide bearing only measurements because we are using passive sonar. So what we are developing is a cooperative autonomy and data fusion framework because we think they are the key driver to improve the detection, classification, tracking, and localization performance. And how to do that? So we are developing an occupancy grid mapping framework that will be the basis for cooperative behaviors. Based on experimental trial that we had with these Perseus volumetric arrays, we have developed a sensor model, and this sensor model is used to create this occupancy grid. In each of these grid, the color of the grid means the probability that a target is a certain place. In this case, yellow, let's say, is good, and dark blue is bad. As you see, we have a beam of yellow because you have just bearing measurements. And so using these maps, they are useful because they can drive our area survey because they give us information about places that are likely empty, dark blue, likely full, let's say contain a vessel, yellow, and they are to be explored, that is a light blue. But it's not enough because we want to localize the target. So the vehicles share data, and here you can see the shared map, and here we use the Laplacian operator, and we search for negative values of the Laplacian operator. It means that the two maps has some peaks of probability, and these are the geometric configuration that we want to search. And how to do that? We propagate into the future the possible maps according to different decisions of the robot, and the robot cooperatively decide their movement to create this kind of good, from our perspective, geometric position. And how to bring that in the field, because it's always difficult to bring this kind of stuff at sea. So the first step is to make the wave glider fully autonomous, because as you probably know, the wave gliders, when you buy the wave gliders come with a so-called front seat computer that is usually controlled via satellite Iridium messages. So the idea of the wave glider is that if you have some autonomy, the autonomy runs on board the command and control station or on board the support vessel and not on board the vehicles. There is no integration between a possible backseat computer that you install on board for signal processing or for communication managing and so on with the front seat. What we have done is that we have installed the backseat computer on the robot, and we have integrated this backseat computer with the front seat. And this is important because in this way we can bring the autonomy directly on board the wave gliders. We have, you can see there some results from last cruise in December, in which our ICADME control architecture that is using in this case the MOOS and the PHELM IVP is able to control the wave glider along 4 waypoints and also handling an automatic collision avoidance with a virtual vessel. So the next steps, we are bringing the ICADME multi-task mission control that we are developing at CMRE with the 2 different tasks, an area survey based on occupancy grid, and the target localization task, the algorithm that I showed you before that we have developed in MATLAB, and we will test that in the REPMUS trial in next September in Portugal. And this will lead to the final system test that we will have in February 2022, in which we will integrate the global view, the camera and the sensor in a simulated use case of interest. And now briefly, the second project I'm working on, this is the METRICS project. METRICS stands for Metrological Evaluation and Testing of Robotics International Competition. It's a project on robotics competition. The idea of METRICS is to design and organize competition as reproducible and objective evaluation campaigns as much as possible. And we are doing that in 4 different areas: for healthcare, agile production, agri-food, and inspection and maintenance, the RAMI competition. As a CMRE, we are in charge of the RAMI competitions, the marine segment, because there is also an aerial segment organized by CATEC in Spain. And for the marine robots, we follow our tradition of organizing a marine robotics competition. So the RAMI competition will be held in the CMRE water basin in La Spezia. The area is 50 meter by 50 meter and is a protected seawater area with a depth of 4 meters. The important thing is that it's a sort of unique conditions in the world for this kind of underwater robotics competition. So teams have to face realistic conditions in terms of salinity, tidal waves, and changing of illumination and so on. In the area, we have created different objects of potential interest related to the inspection and maintenance task. So you see there manipulation console, pipes, some colored buoys, some numbers, and so on. And which are the tasks and functionalities we are going to present? So we are going to present some tasks, three tasks that we call task benchmarks and 3 functionality benchmarks related to the task. These tasks are essentially an intervention in an area where something happened. An area survey of different tasks. You can see here the most complex task. It is the robot arrives, inspect the colored buoys, and then inspect the manipulation area, and then it will close some valve. During the robot has to be fully autonomous during all the mission, but during the manipulation, it can be tele-operated. And which are the next events and next dates. So we are also working to the preparation of a virtual competition. Both because we want to prepare teams to the perception task, because in our experience, we have seen that when the teams arrive to the real physical events, they are overwhelmed by practical problems, let's say motors that don't work and so on. So we want to have them focused on perception, algorithms, and so on. Then we want also to attract people outside of the marine competition, people from AI. Now there is the boost of AI. And third, obviously, because there has been this sad international situation in which physical events are not allowed. So what we have done, we have created the data set from images collected at sea. We have divided them in 5 different classes. That is colored buoys, numbers on pipes, numbers on the console, real damage marker on pipe, and the rest, let's say. And we will have labeled that, and we will propose this training set to the teams. And the teams, when they have set up their software, the software will be evaluated on a validation set. And this is important because these are the same OVPIs that they will find in the physical event that we will have, hopefully, I hope we will have that, in summer 2022. So thank you for your attention. Here are the contacts, and I will leave you, if it starts with a video about the deployment, and I'm here to take your questions.
Thank you very much, Gabriele. Thank you. I'm sorry we have to rush, but again, at the end, we'll have questions and answers. So okay. After you're done with the video, we'll start with the next presentation by Peter Trslic, University of Limerick, entitled Rapid Risk-Aware Automated Port Inspection Drone. Thank you very much, Gabriele.
Yeah, hello everyone. I hope you can hear me.
Yes.
Yeah, that's great. I'll just start the presentation now. Yeah. So, hi everyone, I'm Petar Trslic. I'm research fellow at Center for Robotics and Intelligent Systems back in University of Limerick. So, I present today the RAPID project, which stands for Risk-Aware Automated Port Inspection for Drones. First, I'll just do the quick introduction of the group, and I'll show how our role and expertise contributes to the whole RAPID project. So the Center for Robotics and Intelligent Systems was founded more than 20 years ago in 2000s and consists of between 20 and 30 people at all times. And mostly the center deals with underwater robotics for more than 20 years. And in recent, maybe 5 to 6 years, we start dealing with aerial robotics as well. So fleet consists of various ROVs, from small video arrays to ROV built-in house, which is IROV, approximately 1 meter long by 67 centimeters width, and all the way to the big world-class ROV, which is Comanche ROV. So the whole system is 1.5 ton. The robot itself and the whole systems with launch and recovery system and the cabin approximately weighs 20 tons. Here we can see the video from our latest ship time. We did some laser scanning off the coast of Ireland. This is a battleship from First World War, one of the biggest one, Audacious. And we were actually doing a live stream on the YouTube. We had a historian and the diver in place who were then talking over our laser scan. Here we can see one laser line that we did. We were doing long laser lines along the shipwreck, so 180 to 200 meters long. We still didn't process the data, so hopefully we'll have nice 3D model. So let's just continue to the drones now. So we also have various drones, from parrot drones, which are great for just initial testing indoors, to real workhorses like DJI M300 and M600. We developed some of our drones, and our biggest drone is actually CGT-50, which is vertical takeoff and landing drone, which then proceeds into standard flight. It has a petrol engine and autonomy over 500 to 600 kilometers. We're using those drones for photogrammetry, LiDAR scanning, 3D reconstruction, and also developing of various control algorithms. So how do we contribute to the RAPID? So what's the RAPID project? So RAPID started approximately at the end of the last year, so we're early in the project. The goal of the project is detection of critical deterioration in transport system infrastructure, while trying to minimize system disruption and delays. So traditionally, the structural condition and monitoring of the bridges, ships, and other port infrastructure, it relies on a non-destructive visual examination by engineers that are actually there on site. And we know that approximately 9% of all camera inspection data is done by the drones. However, they're all manually piloted, and the process of this fault identification still requires mobilization of scaffolding, scaffolding and elevated machines to support that inspection. And the engineers must physically be there and do actual research, detect for example, tracks in the bridges and mark them. So the whole goal of the project is to automate the workflow. So whole workflow from getting the drone to the site using autonomous surface vehicles to performing inspection and fault detection using machine learning techniques, and all the way to reporting. So here we can see the general concept of the project. So we would have a rapid service center, which then issues command of service requests, like for predictive maintenance of the bridge or some ship. It goes through digital twin. So the whole path of the drones should be calculated and simulated. After it passes that, the whole flight path goes to use space. After the mission is improved, then we can proceed to actual mission, which can be extended using the surface vehicle. There are 9 partners in the project. The project coordinator is University of West Scotland, and each of the partners has a dedicated role in the project. So University of West Scotland is managing digital twin and risk management. We, as University of Limerick, working on swarm robotics, sense and avoid systems, and autonomous flight. SINTEF is there for smart energy management. Thales does machine learning for crack detection. University of Dundee is dealing with the laws and standards which are related to the drones flying, because flying drones, it's much more dangerous for the public, and public does not perceive it as underwater drones. So there is a lot of work to be done there. Revolve and Fraunhofer are working on integrating and validating the assets for inspection and service. And Hamburg Port Company actually provides the whole facilities for actual testing, and they're going to use the rapid project outcomes. And X-Ocean provides then the surface vehicle. So what's the role of University of Limerick? So we are there to develop beyond visual line of sight flight control and mitigation of the risk, develop detect and avoid techniques, develop relative-based navigation in GPS-denied environments, and then one of the most important tasks, autonomous landing to the surface vehicle. Our platform for the project is drone DJI Matrice M300 RTK. So we started with getting data sets. So for machine learning, the goal is, here we can see actually our CGT-50 drone taking off. This drone is approximately 4 meters wingspan and 4 meters long. So it's taking off, and this is recorded from a DJI M300 drone using infrared camera. So the goal is to actually collect the data, infrared data, which we hope to then annotate and use in machine learning to get actually the thermal footprint of the bigger drone or Cessnas and smaller vehicles. So the whole thing is in developing of sense and avoid system, and in both long range, mid range, and short range. So for short range, we would use stereo cameras on the drone itself. M300 drone, there are 8 stereo pairs. And then for medium distance, we would use this infrared camera or zoom camera on the drone with the laser finder. And for the long distance, standard ADS-B would be used. Here we can see initial bridge reconstruction we did with the drone. So this is bridge at University of Limerick. It's approximately 140 meters long. This was not real time, but this was post-processed. obviously, and it is not still the highest details we can achieve, but it's nice to see what the drone can do and what we are able to create. So we can see here something that can be also interpreted as a cracks. So it was the test of the resolution and the details we can achieve with the drone. And the initial flights we have. So we did initial autonomous flights. The goal was just to check how does the whole system operates. So DJ comes with a software development kit, and the SDK is there for flight, for camera, and for mission planning. So it's really capable. However, there is a lot of errors in the code. So there is a bit of debugging that has to be done. So here, yeah, it's just we're tested like feeding in, detecting our RUCO marker, feeding in, processing it, and feeding in positioning for the drone. This is just first test. Here at the bottom, we tested the zoom camera. That's one of our payloads. And this camera has 20 times optical zoom and 200 times digital zoom. This is filmed from approximately 50 meters height. And if I speed it up, so this structure here that we're gonna zoom in, it's a cement factory. And this is approximately 9.5 kilometers far away from the place where we recorded. So now it's gonna zoom in a bit more. So it's incredible the amount of stabilization and image quality you get from the product. Later on here, we zoomed in into this is Church Tower. The church is approximately 3.5 to 4 kilometers far away. So let's say half of the distance of the cement factory. So we can see what the system is capable of. So now, yeah, we need to proceed with developing of autonomous flight and other algorithms, but we are now at this stage of the project, we are sure of the capabilities of our platform. So that's pretty much it for me. Thank you very much. I hope I didn't take too much time. And if you want to contact me, please send an email or check our website. So thanks.
Thank you, Petar. Okay, so we have essentially reached the end of the project session because it's about 10:40. So we have to bite into the break time. The break lasts for 20 minutes. So I suggest that we have discussions for a period of 15 minutes, if you don't mind. And then, sorry about that, you may have a quick coffee. So let's start with the questions and answers. Again, you can either raise your hand or write the questions in the chat box. Thank you very much. So we are waiting for questions. I'll start with one for Gabriele. I quite enjoyed your presentation, namely in what concerned the cooperative target tracking and localization. And so apparently used bearing measurements. Were you ever interested in the problem of doing so, but using only range measurements?
Yeah, yes. In previous work, we have worked on active sonar with underwater vehicles. And there we have range and bearing measurements. So now we are trying to develop also autonomous, and we have autonomous cooperative behaviors for that. But in the passive one for this application, we have just bearing measurement. So the idea is to try to mix that and to bring that on different platforms, because in REPMUS, we will try that with underwater vehicles, towing some hydrophone arrays. But let's say the objective is to develop something that is in some way generic, and then we adapt to the different platforms. Then using only range-only measurement, it's another task that we can explore into the future.
Thank you.
You're welcome.
So, any other questions, please?
And we are, sorry, we are using something like that for the deep water navigation. obviously, but that's another story.
You mean deep water navigation?
Yeah, we have used to have some network with some beacons, and we have done just in December. We have tried to use a one-way range measurement. Usually we use two range measurements, but it worked, but it was not so good when communications was bad. So we needed something more. So we tried to see if a one-way range approach could work. So we had a good result in let's say in a good scenario, let's see. But however, it's a first step. And in next oceans, we produce the first results.
Okay, thank you. Questions, please. Giovanni and Iveri.
Hi, Antonio. Thank you. I have maybe a technicality, a small question for Thomas Vogele. I found the presentation very interesting. And I was wondering regarding the deep learning approach, whether they have any specific task related to handling of outliers in sensor data, because I could guess they might have several, especially for multi-sensor systems. And if they do have a task or a work package or any kind of work in that area, I would be happy to have a pointer.
I'm afraid I'm not the right person to answer this question because my colleague who is working on this, I can point to him. We're still working on the concept. I'm sure they have the algorithms and measures to take care of these outliers, but I can't help you with this at the moment. Sorry about this.
Oh, no. Well, just a pointer to the project will be fine, Thomas. Thank you.
Okay, I'll get you in touch with him. Okay.
Thank you very much.
So I have a half-finished question in the chat box from Minehiko. Could you please complete or? So this is a question for Andry. Have you achieved cleaning using AUV in order to carry out contact CP measurement?
Sorry, Antonio, can you repeat the?
Yeah, so it is written as follows. Have you achieved cleaning using AUV in order to carry out contact CP measurement? I'm not sure what this means.
Cathodic protection, probably. We are in Atlantis. We have two approaches. One is we are using ROVs with an arm that will perform some cathodic protection measurements, but also cleaning. And we have an intervention AUV from University of Girona that will also provide some capabilities, manipulation capabilities for cleaning the cathodic protection, because when an infrastructure is on sea by many months, the biggest problem is to measure, because with the accumulation of biological growth, most of the time it's almost impossible to measure directly the volume loss of the catheters. So we need to clean the surface. Okay? So in Atlantis, we will demonstrate both technologies, okay? Autonomous vehicles, but also remotely operated vehicles, okay?
Thank you. So any questions at this point? Okay, I have a question for Thomas. So I saw in your presentation said that one of the topics being addressed is the one of sort of interaction between robots and human divers. And I'm just curious, it's a general question. I'm just curious as to what is the resemblance or the innovation beyond what has been done so far within the group of Nikola Miskovic in Croatia. So going back to the CADI project, I was also involved in that, but more recently they have continued to work in this area. Yeah,
I guess the application is similar to the one of the CADI project, as far as I know it. What we're focusing here is really on the perception. So the idea is really, if you have diver, I mean, we're working here with the technical Trslic, what's the English name for that? It's kind of the disaster management network of in Germany here. And, you know, when the divers are in action, they usually do kind of welding and boring and sawing underwater. So they create a lot of turbidity. So if the water is maybe still, if there's some vision there before you start the work, but after and while you do the work, it definitely goes away. So the problem is you cannot watch these divers while they're doing their job. And this is mainly the focus of the project, to enable perception even under these conditions. And of course you can use sonar to do this. If you have no visibility, you can use sonar, but usually the sonar vision is not very, very good. The quality of the sonar data is not so good. So it is to improve the quality of these data. That's the purpose. So I guess the application area is pretty much the same, you're right, but we are focusing on the perception aspect.
Okay, so we have another question coming from Giuseppe Casalino for Thomas, but he's not done writing yet. So Giuseppe, Pino, speed up. So it's coming. Pino, if you wish, you can say it on the screen.
I try. Can you hear me?
Yes.
Okay, no, it was just a very technical question for Thomas Vogele. I was guessing if in their integration of their complete neural network that has to fuse sonar data, visual data, and so on, if they are relying on some, let's say, already available tools like a quite popular one like YOLO and others, or if they have to instead to restart in a sense, scratch, or integrated, also different field of view, you know, sonar, acoustic, and so on. I mean, how the consortium is oriented to do in this very interesting objective.
Yes, well, I'm not sure if we use YOLO for this. We would definitely use build on existing work that was done in our institute and in the other institutes. So we're using already kind of proven algorithms and try to improve them. You probably have to get in touch, as I said, with the deep learning specialists in the project to see what they really use. I mean, which neural networks they want to use. I think at the moment we're still also experimenting with this. As I said, we are still in the conceptual phase. We have some ideas. We're collecting data and setting up frameworks to collect data. And I think we still have to decide on which solutions we will use. We'll definitely test several of them and then try to identify the best one. But this is of course part of the project.
Okay,
right, to identify suitable tools. So if you have any suggestions, feel free to share them.
Okay. So Nuno, gracias. Go ahead, please.
Thank you so much.
Hi. Okay. I was just going to add something to what Thomas was saying there, and just picking up also on Giovanni the very
question from before. So basically, exactly what Thomas was saying. We actually, this last few years, in these terms of neural networks and deep learning approaches, has been quite a convolution in terms of changing of paradigms. And we are looking at things that go actually beyond the CNNs this year. So, for instance, one of the problems that we are facing with this case of intercessoric learning is that we lacking a lot of data, but also we're lacking a lot of well-registered data between the sensors. And this, picking up what Giovanni was asking, generates definitely a lot of outliers. So one solution for this that we're looking is not on totally supervised learning methods like traditional, let's say, CNNs, but self-learning networks. That is something that appeared, started being popular last year, which are really poised to help us in this case.
Thank you, Nuno. Good to see you.
Great to see you.
Okay, so if there are not any questions at this point, then we should stop because we should allow ourselves some time to have a coffee. So now I will hand over the baton to Gianluca Antonelli. The session will start at 11 o'clock. Thank you very much to Richard, Andry, Thomas, Gabriele, and Petar for making this a very, very interesting session. Thank you very much. So see you soon.